Okay, so now we can move on to question number 2. So part A says to draw a Lewis structure for the ozone molecule O3. The order of atom attachment is 0, 0, 0, and they do not form a ring. So they just gave a little hint. Chemists used ozone to cleave carbon-carbon double bonds. Part B is to draw the contributing resonance structures, including formal charges. Part C, how does the resonance model account for the fact that the length of each oxygen-oxygen bond in ozone, which is 128 picometers, is shorter than the oxygen-oxygen single bond in hydrogen peroxide, which is 147 picometers, but longer than the oxygen-oxygen double bond in the oxygen molecule, 123 picometers. Okay, so first let's draw the Lewis structure of ozone. So when writing Lewis structures, I like to first find the total number of valence electrons in the molecule. So I'll just say total valence electrons. For one oxygen atom, there are 6 valence electrons, and since we have 3 of them in ozone, we multiply this value by 3. So this gives us a total number of valence electrons of 18. Okay, so now I'm just going to draw my 3 oxygens in a line like that. So let's recall that each bond contains 2 electrons. So far I've only written 4 electrons out of the 18. So I'm going to make one of them a double bond. And then I'm going to fill out the rest with all of the lone pairs on oxygen. So this has a double bond. So I'm just going to write 4 valence electrons on the oxygen on the left. And in the middle, it has a double bond and a single bond on its right. So for a full quartet, I'm just going to add a lone pair at the top there. And then for this singly bonded oxygen, I'm going to draw all of its lone pairs. And then I'm going to show the charges for each of the atoms. The one in the middle has a positive charge, and this one at the end has a negative charge. Okay, so now let's count out all the electrons present in this molecule. Counting all the lone pairs, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now I'm going to count all the electrons in each bond. So there's 2 in each bond. So 13, 14, 15, 16, 17, 18. Okay, so all of the electrons are accounted for. So that is one Lewis structure. And we can also show this oxygen on the left having the single charge, the single bond, and the oxygen on the right having the double bond. So it's basically the same. The one in the middle will still have a positive charge, but this time the oxygen on the left will carry the negative charge. So I can show another resonance structure. If I bring this negative charge down, to to get 2 double bonds and all of the oxygens being neutral. Okay, so the last part says, how does the resonance model account for the fact that the lengths are all different? So for ozone in particular, for ozone, there is a mixture of both S and D bonds. So single and double bonds. Just write it out then. So that's why its length is 128 picometers. So hydrogen peroxide it is 147 picometers. And this is because single bonds are longer, typically, than double bonds. So when we have an oxygen molecule, which only has the double bond, it will be much shorter than the length of the oxygen-oxygen bond in hydrogen peroxide. But since ozone has a mixture of both single and double bonds, it kind of puts it in between the two of the other molecules. Okay, so let's see what the junior tutor said. The Lewis structure for ozone O3 is as follows. So they have the double bonded oxygen, and then one in the middle, and then a single bond. The resonance structures of ozone and their formal charges are as follows. Yep, so they have something similar. They also included, maybe I should have also included a resonance structure kind of in the middle. Showing that you could have a partial double bond as well. Yep, so that's basically the same thing I have. And you can show that the double bond can be on the left oxygen or it can be on the right. Or you could have all 3 of the oxygens having a double bond. And for part C, the junior tutor said ozone bond lengths were found to be 128 picometers. A single bond would have a longer bond length than a double bond, but in ozone, we find that the bond lengths are equal. This means that they are a mixture of single and double bonds. This is why the bond length is less than that of an oxygen-oxygen single bond and more than that of an oxygen-oxygen double bond. Yep, so this solution is correct.